Good afternoon. Thank you for coming. I'm Pooja Dewan from BNSF Railway. I'm the chair of the Innovative Applications in Analytics Award. And welcome to the third session and the third finalist for the award. The third applicant is from MIT, Chris Johnson and Dr. David Simchi-Levy. They'll be sharing their work on the work that they did in analytics for an online retailer, Rulala. Just a couple of housekeeping items. This is a 50-minute session. We try to give 35 minutes to the contestants to just present, so no questions during the contestants' time. And then the first chance to ask question goes to the judges sitting right here. And if we have time permitting, then I'll open it up, the questions to the floor. But if we don't, hopefully they can address any of your questions later on in the break time. This session is being recorded, so please be aware about that fact and limit the movement across the room. And please put your phones on vibrate. Thank you. With that.
Thank you. Welcome, everybody. I'm David Simchi-Levy. I'm on the faculty at MIT. With me is Chris Johnson, a PhD student at MIT as well. This is a joint project with an online retailer called Rulala. With a show of hands, how many of you know Rulala or use their product? Yeah, a few. We will have an opportunity to hear from the VP of pricing and operation strategy later on in the talk about some of the challenges and what we have done together with Rulala. Rulala is in the online flash sales industry. In this industry, retailers offer deep discounts for a short period of time. For example, Rulala offers a discount for 48 hours. This industry was established in the mid-2000s, and it's growing now at a rate of about 70% per year. The aggregated revenue across the retailer in this business is around $4 billion. You can see on the slide the key players in the US, Guild, Zulily, and Rulala. The one on the right-hand side is a large European online retailer in the flash sales business. And on the left-hand side, you see a Chinese company that has been quite successful. If you log into Rulala website right now, you will see a screen like the one that I have here. They will say, we are running an event right now. We are offering products like classical watches, jewelries, men running shoes, women running shoes. And the website will highlight the remaining time until the event is closed to generate a sense of urgency. If you are interested in one of the products, say you're interested in women running shoes, you click on the product and it will take you to another screen where the website shows different styles and will emphasize the price that Rulala sells their product for. On the left-hand side of this price, there is another number representing the recommended price by the manufacturer. And again, the idea is that we generate a sense of a deep discount offered by Rulala to its customers. Suppose you're interested in one of the styles. You click on that style and the website will show you the available sizes. And now the customer needs to make a buy no buy decision, right? And finalize the process. Rulala operation is very simple. Their buyers will decide what product to buy from different manufacturers like Louis Vuitton, Ralph Lauren, Nike, and the like. We will focus here mostly on fashion products. The items arrive at their warehouse, and then the buyers need to decide when to sell the product and at what price. And so they identify the event where they sell the specific product. During the event, items are sold. If everything is sold during the first time this product introduced to the market, then it's over. All the inventory was consumed. If not all the inventory was consumed, was sold, then the inventory will stay at their warehouse for 6, 7, 8 months until another event where they sell the same product. And the reason for that, this constraint is imposed by the manufacturer. Manufacturers do not want their product to be discounted too frequently as a result. It's important to optimize performance during first exposure, during the first time this product is introduced to the market, but this is the most challenging time because you have no historical data about customer demand. And so let's hear the VP of Pricing and Operations Strategy talk about some of their challenges.
Hello, my name is Murali Narayanaswamy. I'm the VP of Pricing and Operations Strategy at Ulala. The project that we worked with MIT on was to optimize our primary pricing for fashion products. And I have to reiterate that this was an amazing project. It was fun working with the team, but more importantly, it was a really useful tool that is going to, we feel, fundamentally impact our business. So Ulala is a $500 million retailer, primarily focused in the US. We cover a bunch of different product categories, with primarily women's fashion, which is women's apparel, contemporary traditional, accessories, European luxury fashion. But we also carry men's fashion, home goods, and kids products. We have a member base of about 9 million. And as I said, we're primarily US-based, but we recently started shipping to international locations as well. So now let me get into the pricing process itself. Pricing itself has a couple of components to it, right? So the first component is, what is competitive pricing? Competitive pricing requires us to go mine price data from our competitive websites and sometimes physical stores too, to essentially figure out what the price point of a similar style is. In fashion, unfortunately, it's very hard to find that same product in any website just because of the way the industry works, right? So brands make the products differently for different retailers, and it is very hard for anybody to go find the exact same product somewhere else. The problem that is not well studied and well understood, and there are not good tools out there, is about how do you set the price of the first exposure for fashion products that you cannot very easily count. So that is what the fundamental problem we were tackling with this project. Today, in the absence of a tool, the merchants would try to hit their margin targets. They would price on a cost-plus basis. They would take the cost from the PO. They say, here's the target margin they're trying to hit, and they'll calculate their retail price. Ensure that the retail price calculation is sensible. They want to make sure that a category of products is priced in the range of that category for an off-price retailer. They make sure that it's sensible, but otherwise that's about all they do. They do not differentiate between specific styles. They try to net out a margin target at the overall pivot level, and they have no ability to differentiate between styles. But in order to optimize prices, our hypothesis was that there are certain observable attributes for styles that could be used to figure out which ones do well versus others. So the first step in this process was to actually look at our existing data to see what styles, what the performance of sell-through performance of styles were. And this is the chart that Chris is actually showing you on the slide. This shows you the sell-through distribution by styles. Before we get into the chart itself, what is sell-through? Sell-through is a metric that we use to understand the sales performance of specific items. And sell-through is defined very simply as sales units divided by the supply units that you had. So let's say for a specific sweater, we had 100 units of the sweater that we purchased from the brand, and we exposed that sweater in an event. And 60 units of that same sweater actually sold out. The sell-through for that item is 60 divided by 100 and 60%. So we calculated this sell-through for every style and then created a histogram of what percentage of styles fall under various sell-through buckets. So the x-axis here shows you the sell-through bands, 0 to 25, 25 50, 50 to 75, 75 to 100, and completely sold out. And the y-axis shows you what percentage of the styles actually fall under that bucket. So what this chart showed us was a very interesting finding that we didn't know ourselves, was 50% of our styles actually sell out in the first time that they are exposed to the net. Now that showed us that there was an incredible value in being able to predict which styles would actually fall in that bucket, because that gives us an opportunity to price higher on those styles. It also shows you that 50% of the styles don't sell out, which means that when we buy to a certain target sell-through, our merchants don't really know which styles are actually going to be selling out and which styles are not going to be selling out. They just play a portfolio strategy and they buy a bunch of styles, and 50% of them work and they sell out and 50% doesn't. So the question then is, if the human being cannot find out which styles are going to sell out, can a computer find out? Right? And that was the question that we posed to Chris and the MIT team. And that prompted kind of kicked off this whole project. And Chris went and created a regression model based on a bunch of observable attributes that helped us create a demand prediction model at a style level, which was the foundational model for the whole price optimization.
Great. So as Murali mentioned, the main objective of our project was to maximize expected revenue of these first exposure styles or new products. And we did this in really a two-pronged approach. So we started with demand forecasting model, and if we could do that well, then we can use demand forecast as an input into a price optimization model. So I'll spend the next few slides talking about the demand forecasting piece and then move forward. So the main challenge here, and kind of what both of them had said, is that we're trying to predict demand for styles that Rule Allah has never sold before. So we can't use any of the standard techniques like a time series analysis or that kind of thing that you might be familiar with in the literature. So what we could do is we could use a lot of the data that we had before, styles that we sold in the past, and try to identify features from those data or those events, and map the features from data, styles that we sold in the past to styles that we want to sell tomorrow. And in that way, we can use demand information from what we sold in the past to predict demand of what we're going to sell tomorrow. So here are some of the features that we use in our regression model. I'm not going to go through all these, but on the left, there's some that are related to products. So things like how popular the brand is or the color is. Over on the right, you have some features related to the timing of the event. So did this event start at 11 a.m. in the morning or 8 p.m. at night? Did it start on a weekend or a weekday? And some of the most important features, as it turns out, are the ones in the middle. So as you might imagine, price is a good predictor of demand. Percent discount, this is a discount off of the manufacturer's suggested retail price. The number of similar styles in the event, so are you seeing 3 different pairs of running shoes on the web page at the same time, or are you seeing 300 pairs of running shoes? This one here actually ended up being the most important feature in our regression model, and I'll talk about it again later, so I want to spend some time on it. We call it this relative price of similar styles, and we define it as the price of the style divided by the average price of all the other styles that you see on the web page that are in the same class, so all the other running shoes. And what we're trying to capture here is a reference price effect that you might have as a consumer when you see different styles on the same page. So for instance, Rule Allah might be selling 10 running shoes, say. They could price them all at $100, all the same. And I might, as a consumer, go on and say, oh, that's a pretty good deal. I think I'm going to choose my favorite of the 10 running shoes. Alternatively, they could have priced 5 of those running shoes at $80 and 5 at $100. Now, all of a sudden, the same 5 running shoes that were priced at $100 before, they're still priced at $100, but I don't think it's as good as a deal anymore because I see other running shoes on the same page priced for $80. So that's the kind of thing that we're trying to capture with this relative price of similar styles feature. So for those of you guys familiar with the terminology, we randomly divided our historical data into a training and a testing data set. And what you do is you apply a bunch of different regression models to your training data. We applied the ones listed here and some others. So linear, power, and semi-logarithmic regression. These are all common for aggregate demand forecast regression models. And then we applied some other ones as well that we haven't seen used in aggregate demand forecasting literature, and things like regression trees, neural networks, SVM, these type of techniques. And we use out-of-sample testing, so we use our testing data set in order to really choose the model and identify which model we should use. We use about half a dozen different performance metrics. And what we thought was really interesting was for all 6 performance metrics that we used, regression trees actually outperformed all of the other regression models. And again, I think this is interesting because we haven't seen regression trees being used for aggregate demand prediction before. So for those of you that might not be familiar with regression trees, I'll briefly describe what they are and then say a few words about what the intuition is as to why we think they work well in our setting. So this is an example of a very simple regression tree, not the one that we actually use to predict demand. And I want to explain how you would predict demand for a style that you're going to sell tomorrow using this tree. So I start at the top of the tree and I say, okay, if this condition is true, so if price is less than $100, then I move left along my tree, and otherwise I move to the right. So say it's true, then I move here and I say the relative price of similar styles less than 0.8. In other words, is the price of this style less than 80% of the average price of all the other styles on the page? And if that's true, I move to the left again. When I get to the bottom of a tree, I have my demand prediction. So I would predict that I'm going to sell 50 units tomorrow. Where is this 50 coming from? This 50 is just the average demand of all styles that I've sold in the past with these same features, so price less than 100 and relative price less than 0.8. So in a sense, what a regression tree does is really partition the styles that you've sold into the past into different buckets. So some that end up here, here, and here, and they're partitioning it automatically. These are built, I didn't choose that price less than 100 is the first split. They're built automatically, and it separates your data that way. And this really leads into, I guess, our main intuition as to why we think they work well in our setting. And that's because essentially what we're doing when we're using these to predict demand is just using the set of styles that you've sold in the past that are similar or comparable in some way to the style that I want to predict demand for tomorrow. Another piece of intuition we have as to these regression trees working well is that they allow for what we call this non-monotonic relationship between price and demand. So a lot of the standard demand forecasting models require that as you increase your price, your demand is going to decrease. That makes a lot of sense for a lot of products, but it's pretty well known that for fashion apparel and accessories, that's not really the case. So sometimes you'll see as price increases, you might actually have demand increasing as well. And regression trees allow for these type of non-monotonicity patterns. All right. The one thing that I haven't talked about was how do we come up with this demand number of 50? I mentioned, okay, it's the average demand of everything that falls under these features that I've sold in the past. But what do we use for demand? So a lot of companies can use sales as a proxy for demand, and that works fairly well as long as you're not stocking out. But if you remember with the graph that Merrily showed, we're actually stocking out over half of the time. And so we can't use sales as a proxy for demand in this case. So we need somehow a way of estimating demand, which would be sales plus an estimate of what we call lost sales during the period of stock out. So let me describe this challenge a little more and what we did to address it. So this is an example sales curve, is what they call it, for a product that did not stock out. It's a 2-day event, so on the x-axis you have hours into the event from 0 up to 48 hours, and on the y-axis here you have the percent of total sales. And the way that you read this, you might say after 4 hours into the event, I've sold about 40-45% of what I sold for the entire 2-day event. And in this case, since we didn't stock out, demand equals actual sales. So now compare this to over half of the case, we have sales curves that look like this. And here for this item, we stocked out 10 hours into the event. And you can imagine that this curve, if I had unlimited inventory, should look more like the other one and continue beyond this 10-hour limit. So in this case, our demand would be actual sales during this first 10 hours plus some estimate of lost sales from 10 hours to 48 hours. So we need to estimate in this quantity in our historical data. So what we did was we used data for items that didn't stock out, so the first sales curve that I showed, in order to predict lost sales for those items that did sell out. And for each event length, so 1, 2, 3, or 4 days long, we aggregated sales based on a set of characteristics. So things like the department, the event start time of day, the day of week, so weekend, weekday. And we created sales curves for each set of characteristics. And this ended up resulting in hundreds and hundreds of sales curves. Some of them didn't have that much data in it, so as you can imagine, there's some noise kind of around the sales curve, and it's not very interpretable if you have that many. So we use clustering. It's a type of descriptive analytics to help further aggregate these curves. So I want to show the results just of the 2-day events to give you an idea of what's going on. Again, we have our hours into the event on the x-axis, the same percent of total sales on the y-axis, and you can see that the clustering results really just separated the products based on the event start time of day. So they have 3 times, 11 a.m., 3 p.m., and 8 p.m., and the day of week either being a weekend or a weekday. And to illustrate kind of what's going on in these curves, just look at the blue one. This is for 8 p.m. events. You can see that after about 5 or 6 hours into the event, this curve really flattens out. And this is, so it's a US retailer only. So this is really when United States folks are typically, hopefully, asleep by then and not buying anything. And then you get another peak in your sales after everyone starts waking up, and really at the 11 a.m. time frame. And 11 a.m. is when most of their events start. And so that's when most of the traffic comes to their site. So look at the black curve. This is for items that started 5 hours after, 5 hours before the other one. And you can see that really the curve just shifted 5 hours to the right. So the flat part of the curve is now shifted 5 hours over. So the results of the clustering make sense in this case and really follow the traffic patterns of customers to their site. Now, how do we use these sales curves to estimate lost sales? It's pretty simple. So just a quick example, say we have an 8 p.m. event that had 100 units in inventory, and we sell out after 5 hours. So the sales curve tells you that if I had unlimited inventory, after 5 hours, I would have sold about 50% of what I would have sold the entire event. So I simply do the division and say, I would have sold 200 units if I had that much in inventory. That's all I want to say for now for the demand forecasting piece. So now that we have demand forecasts, we can switch gears from what I would call kind of the predictive, descriptive side of the analytics and start talking about prescriptive analytics in terms of price optimization. So how can we recommend prices for them to actually use on the site to maximize revenue? Here. So the complexity arises from a feature in our demand forecast, actually. So recall that there's 3 different features that are related to price. Price itself, you have percent discount off MSRP, which is just a function of price, and then this relative price of similar styles. And it's this last feature here, the price divided by average price of similar styles, it's this part that requires that we actually have to optimize all of our prices concurrently on the page. We can't set a price for one product in isolation without thinking about the other prices. So a very naive approach to do this would be to enumerate all the possible price combinations you would have for all styles on your page, forecast demand, calculate revenue, choose the set that gives you the highest revenue. But even for a dozen products, this is going to take days to do. And IAAA often sells over 100 styles on the same page, so we can't wait a year in order to price the next products for tomorrow. So we needed to come up with some algorithm to do this faster. And our key observation was really that demand actually only depends on the average price of all the similar styles on the page, not every style's individual price. So just a little bit of notation. We'll have N is the number of similar styles. So is it 3 styles, 3 running shoes, or 300? That's N. And K is the sum of prices of all the styles. So our average price is obviously K over N. And our relative price of similar styles feature becomes price divided by K over N. And IAAA dictates that all of their prices have to end in this 490 or 990. If you're familiar with retail, this is fairly standard because it signals to the customer that they're getting a good deal. So we have a finite set of possible prices. This means that we have a finite possible sums of K here. So there's a finite number of possible Ks. So how can we use this? Well, one thing we can do is we can formulate an integer optimization problem for every value of k. So we have a bunch of these, each for your possible values of k. I didn't write the actual math down. If anyone wants to nerd out afterwards, I'd be happy to. But the idea is you want to maximize revenue in your constraints. One just says each style has to be assigned exactly one price. That's obvious. The other one is the sum of prices of all styles has to equal k. So one approach could be solve this optimization problem for every value of k and choose the one that gives you the maximum revenue. The problem is for the larger problem sizes, this still took several days to solve. And Rulala has to price hundreds of new products on a daily basis, so this still wasn't good enough. So what we were able to find out was that we proved that the optimal objective to this integer program, and the difference between that and the optimal objective of the linear program relaxation is very, very small. In fact, it only differs by the revenue associated with a single style, independent of problem size. So for the very large problems, you're very, very, very close by solving the linear program versus integer program. And we can use this to develop an efficient algorithm that solves to optimality, not a linear programming kind of a solution, but solves to optimality. And the average daily runtime is only 45 minutes. And the longest we've seen it take was less than 5 hours. So this is something that they can use on a daily basis. I'll pass it back over to David now. He's going to talk about the software that we developed in a field experiment that we ran after.
Thank you, Chris. So let me start with a discussion of the implementation and then take you through the impact and finalize with observations from Rulala talking about the impact on their business. The implementation included focusing on their ERP. Every night, our system sucked in data from Rulala database and move it to the optimizer database. We feed this information to a script that we wrote using R to generate the regression trees. And we generate hundreds of regression trees in the process. This is fed into the optimizer. Remember, we are solving a mixed integer program. To solve it to optimality, we start by solving the LP, and then we have a way to close the gap between the LP and the mixed integer program. At the end of this process, we feed all the prices to the optimizer database, and in the morning, this is fed during this process, this is fed to Rulala ERP. In the morning, when the buyer comes in, when the merchant comes in, they have an ability to review and override some of the prices. And the only case where they override some of the prices is they have people in the morning looking at competition, at competitors, and if they find a competitor who offers the same product at a lower price, then they will override the recommendation of the tool, and this happens very infrequently. And the main objective for this, the main reason for this is Rulala want to make sure that they are the number one low-cost online retailer in that space. So for almost all the products, things are approved, but those that are not approved, it will be because somebody found that a specific product is offered by a competitor at a lower price. So we did a lot of offline analysis to convince ourselves that this should work, but the key question was what will be the impact in a field study? At the beginning of 2014, we ran a 5-month field study where we identified 6,000 styles where the system recommended an increase in price. And there were two objectives for the field experiment, where basically our system is running pricing for Rulala. The first objective is, as you can imagine, to see what is the impact on revenue and therefore what is the impact on profit, because there is no additional cost. And so whatever I can get on revenue goes straight into bottom line. But there was an equally important second question. What Rulala executives were worried about, they said, look, you're focusing on revenue or profit. We also are worried about not losing market share. And so the question is, can we make sure that as we use the technology, technology, we don't lose demand. We don't lose sales. We don't lose on sales through the way we identified at the beginning. So now, all of a sudden, we have two objectives. One is maximizing revenue and therefore maximizing profit, and the second one is making sure we don't lose on market share. To answer these questions, we split the 6,000 styles into 5 categories, from A to E, mostly by focusing on price point. Category A is the lowest price point, and category E is the highest price point. We further split each category into 2 groups. The treatment group, where we follow the recommendation by the technology, and basically the technology price to the customers, whatever comes out of the optimization. And the control, where we don't follow the technology, we just follow the traditional pricing strategies that the company has. And we tested the null hypothesis that raising prices has first no impact on sales through. We don't lose market share, right? And we use a powerful test, rank sum test, that does not require an assumption on the variable I'm focusing on. So I'm not making any assumption on the distribution of sales through. And as you can see, in categories B, C, all the way to E, we cannot reject the null hypothesis, but we had a problem in category A. Just to realize the challenge that we face in category A relative to the other categories, let's look at this slide, where on the X coordinate, I have the 5 categories from A to E. A is associated with the lowest price, E is associated with the highest price. On the Y coordinate, I have average sales through. Blue represents the performance of the control group, red represents the performance of the treatment group. You can see that there is no difference between control and treatment in terms of sales through associated with categories B to E. But there is a drop in category A, and as you will hear Merle from Rulala talking about the project, we had to adjust our algorithm, still use the optimization, but we had to adjust our algorithm for this, to deal with this challenge. For the other categories, it was just accepted that our tool does not reduce market share or sales for Rulala. What was the impact on revenue, you are asking? This is presented here. For category, on the X coordinate, I have the different categories from A to E. And for the Y coordinate, I'm presenting a percentage increase in revenue and a confidence interval. You can see that for categories B to E, we increase revenue by between 12% to 24%. We had a problem before making the adjustment in category A. The overall increase in revenue on average was about 10%. Merle will describe how we solve the problem for category A. And keep in mind, as you listen to Merle, that when we solve the problem, it's still basically what he is describing is a constraint in the optimization model that we implemented for Rulala. And so let's listen to Merle describing the impact.
The biggest curiosity, I mean, if you raise prices, you're going to raise margin, right? So you're going to make margin rate is going to go up. So that was never the question, right? So the question really, and everybody is concerned about is, if you raise prices, is that going to hurt our demand? The algorithm itself is set up to maximize the revenue dollars. Therefore, if the actuals followed the model predictions, then you would see revenue dollars going up, which is really what we saw. We saw that our results showed a 10% improvement in revenue, and therefore the margin rate came at higher margin dollars. The other goal that we were going after is, as we were saying, we should not be impacting demand. Right? So you could sell fewer units and make more margin dollars. But selling fewer units means that we also have more of unsold inventory sitting on our in our warehouse that we need to still clear through, and it also impacts our relationship with our brands. So there was another objective that was not directly used as an objective function in the model, but is still a business objective, is to make sure that our sell-through rates were not deteriorating. And from the analysis that we have done of 5 months of using the tool, it feels like the sell-through rates are not impacted for a broad range of price point categorizations, except for the really low price points. Right? So anything that is less than $45, it feels like if you raise prices by 10% or 15%, that increase in price is still a very high increase in price for products in that price point, and we saw a deterioration in sell-through, even though margin dollars were high. And so this result was interesting, and so what we did to stem the negative sell-through trend was to cap the price increases to $5. So anything that is less than $50, we would limit the price increases to no more than $5. So overall, we were extremely pleased with the outcome of this project, not only because the business impact was there, but it was also a pleasure to work with this team. They really understood our business, and it is not normal that you see academics really understand the business problems that we are trying to go after, and so this was a breath of fresh air. I have an OR background myself, and I completely understand the value of bringing some of these tools and techniques into making business impact. And this was a classic case study for how we could make this happen for the pricing problem. We are really pleased with this work that we are actually now going to pursue a couple of other ideas with the MIT OR Center in a couple of other areas of our business.
So to summarize, today, if you go on RulerLab website and you buy product, you are basically following a pricing strategy coming out of the analytics that we developed. This analytics that we developed has 3 components, a descriptive analytic component, a predictive analytics, and a prescriptive analytics. Let me talk for a minute about each one of them. The descriptive analytics is all about the use of clustering to estimate lost sales and therefore transfer information from sales to customer demand, right? The predictive analytics is the focus on regression tree. And keep in mind that regression tree, while powerful in terms of predicting customer demand, require you to think carefully about the optimization model. To put this in perspective, think about linear regression. If your demand prediction model comes out of a linear regression, then it's easy to incorporate into an optimization model. But regression trees are really a story, where what the story tells you, if you satisfy this condition or you go along a specific path, this is a demand. But if you go along a different path in the tree, you have a different demand. As a result, we needed to incorporate regression trees into our multi-product price optimization, and this led to the increase in revenue that Merle talked about of about 10% across all their products. I think we will stop here and take questions.
Thank you.